Hello, welcome to another problem session. I've been gone for quite some time, like 2 or 3 months, and uh, and then I feel like uh, it's a good time to restart. So let's see what we have today. Today we have this a problem from Klepter and Kolenko, as you know, Klepner and Kolenko. Let me come back and adjust my settings now. Okay, so the situation here is a very simple one. We have a let me get a thinner print. Yeah, good. So we have a stick here, which is almost vertical. It's a little bit 90. It's kind of a little tilted like that, and just it's a tiny amount more than 90 degrees, not completely vertical. If it's come vertical, it will stay there way if I let go. But it's a little bit like that, and I should do like that, a little bit like that, and then you let go, and it's going to fall, and it's gets into that configuration after some time, and I want to know what is the speed at that point. And for that matter, there is a intermediate situation where it has fallen some angle, say phi, and you can say, hey, of course, different this point and this point will have different speeds. So we can say, look at the center of mass. What's the speed of center of mass? It is falling, v of cm. Okay, and that will depend on how much it has fallen. So over here, this angle becomes 0, or this angle, it went from top to horizontal. So this will, in this case, phi will be 0. I mean, this where the angle I'm doing. So in that case, theta will be 90 degrees. So either of those two angles I can pick, and we can work out what happens in arbitrary time and just plug in theta equals to 90 degrees in the final formula, right? Okay, so what is a clue here? How can we answer this question? Since we're just trying to get a speed, it looks like we can use energy, like energy may be a good idea to use. Maybe kinetic energy good idea to use. So to use kinetic energy or energy conservation idea, we need to look at if it's going to get lost or not. And because it's a frictionless surface, is energy will be conserved, right? Another thing about frictionless surface is there is no horizontal force. The horizontal force is 0, which means if you look at this as an entire body, the external forces on that body is just gravity. So it's just gonna fall, central mass will just fall with the gravity. Just mg is the only external force, which we can take care of using we can take care of gravity through potential energy, you probably know. So basically we have a potential energy plus kinetic energy, and so this is some time t, and this t equal to 0, and this is some t equals to some big T or something like that. This is not asked in the question. It turns out to be a hard problem to get that, but this is just getting v of cm is not that hard. Okay, so kinetic energy at sometime t should be equal to potential energy plus kinetic energy plus kinetic energy at some time t equal to 0, and this is v equal to 0. Now this is a rigid body, so we can kinetic energy will be just center of mass energy, kinetic energy plus a rotation about center of mass. So you can see a center mass used to be here. As it's falling, if you can imagine, all over here it was like that. Over here a little bit later that is like that. So if you can imagine a picture like this in the center of mass frame, if the center of mass and axis is coming out towards us, it's going like this. So t equal to 0, some other t1, some other t2, some other t3, maybe this is the time t. So it's kind of rotating like this, and this angle is the rate of rotation. So d theta over dt is what we used to call omega, angular velocity, angular rotation speed. So that's like that. So this theta turns out to be the right angle to use rather than this phi. Okay. So kinetic energy, going back to it, it's going to have two components. It's going to be half m VCM. So VCM, let's call that just V, letter V, mv square. So V is the V of VCM. Remember that. I'm just trying to simplify notation. And it's going to be half. And because we want moment of inertia about axis to the center of mass, you can get I. This is going to be of a stick of length L and mass m. This half will be 1/12 ml square. That's the moment of rotation about this axis. Half I omega square, and omega is like that. And omega and V will be related. You will see just in a minute. Okay. So that's going to be this guy plus potential energy at time t. Of course, kinetic energy will be 0, so this will be potential energy at time 0. Okay, now let's put some coordinates out there so that we can relate this omega and L and V and things like that. Okay, so let's let me use this as a y coordinate and say this is a t equal to 0, where the CM was over there, and so this is y-axis, and this is at some time t. Half of the L over 2 is this way, half of the L over 2 is that way. This angle is theta, and this is L over 2 this way. And let's call this axis, this y0 equals to L over 2, and this is y of t. So this much is y. We have a y, and we have L over 2, and we have a theta. So V is that way. That's the VCM. VCM, if you look at VCM, is dy dt. So this is y coordinate of the CM that's going, and it's absolute value because this is the speed. Of course, y's value is going down. Dy dt is less than 0, but the speed VCM is okay. It's like that. So I got to be careful with the sign, but because everything is squared, we can be careless and still be okay. All right, so but this kind of relates y and theta. So here y over L over 2 is cosine theta. So we can definitely do a dy dt, which will be let's call it VCM y is equal to dy dt, and that's going to be L over 2 sine theta d theta dt, and this is what we are calling omega, and so, and this is equal to minus VCM. So VCM is equal to this stuff. So we can say, because we just want V, we can replace omega by this. So let's see, L over 2 sine theta times omega VCM, which is of course using letter V for that. So the omega is 2 over L sine theta V. So now it doesn't make a lot of mistake. It makes sure that 2 goes upstairs and L over sine theta goes downstairs. That's correct. So now I just have to simplify this, and I'm going to get a V in there. So that part looks like done. We have to do potential energy part. Okay, to do potential energy part, let me take another ink. Potential energy part. So we can say potential energy equal to 0 when y equals 0. That gives the potential energy formula is just mgy. So yeah, at t equals 0 is over here, at t it's over here. This is y, and this is y equals to L over 2. So this thing just becomes mgy, and this thing just mg L over 2. Okay, and I can see m's are all, you can see m got cancelled from here, 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 so that m doesn't matter, just mass still doesn't matter, so we can just ignore that. So we have gy plus half v square 1 over 24 L square, and this square will be 4 over L square sine square theta v square equals GL over 2. So this is 4, this is 6, and just multiply by 2 everywhere, so makes it 3, 2 here, and that 2 goes away. Okay, so v square is 1 plus the L square goes away 2, 1 over 3 sine square theta equals to G L minus 2y, and we already know y equals to L over 2 cosine theta, so 2y equals to L cosine theta, so I can make it GL 1 minus cosine theta, so everything in terms of angle. So let's see, v square equals to GL 1 minus cosine theta times 3 sine square theta 1 plus 3 sine square theta. I think let's make sure for theta equals to 0, it gives me v square equal to 0. That's correct. When theta equals to pi over 2, this gives me v square is equal to GL 1 minus 0 3 over 1 plus 3, so 3 GL over 4. So v equals to square root of 3 GL. So if you compare that with, say, if I had a ball and it went a distance L over 2, so what's the speed here? Compare this to what we're getting in like a free fall. Free fall, and this was v equal to 0. This is going to be v square 2gh. So this h, right? So 2g times h L over 2. So v would be square root of GL. Over here we are getting square 3 over 2 square GL. So speed is a little bit less, and that has to do with like normal forces opposing it vertically. So I think this is probably correct, and I think you can check your answers. Sometimes although the setup may be correct, I may make some like a silly calculation error. You don't know. You just have to check and do it out. Okay. And whenever you see someone show you a calculation, focus on the a bigger picture, an idea, or how the process was done, rather than like every step has to be precisely correct. Whereas as long as the logic is correct, you can implement the steps yourself. All right. So that's all for now. I will see you in another video. Bye.